All right, guys, let's go ahead and take a look at the warm-up for today. There are two questions here. The first one is a calculation. I'm actually going to do that one second. And so I'm going to talk about the other question first, and then we'll go to the next slide and work out the calculation. So the second question, you've seen this picture before. It says, which has a greater change in momentum, delta P, change in momentum, which has greater force? And so I've got two scenarios there, and they're the same two that we talked about in the notes the other day. Scenario one, we have a truck that comes to a stop because it hits a pile of hay. In scenario two, we have an identical truck traveling at identical speed initially that comes to a stop instead by hitting a wall. So which one would have a greater change in momentum? Which one would have a greater force? This should be in your notes. Okay, what do you guys think? Greater change in momentum? They're the same. Okay, good. Okay, so same change in momentum. And again, it's because it's the same truck, so it has the same mass, and it has the same change in velocity. Now, of course, the rate at which that velocity changes is very different. But if we're looking at mass times change in velocity, that's the equation for change in momentum. And since those two things are the same, we have the same change in momentum. But because they happen over different periods of time, the forces are not the same. Which one has a greater force?
Scenario 2.
Scenario 2, yeah, perfect. Okay, scenario 2 has more force applied to the truck and to any occupants in it because there is less time for that collision to take place. Remember, we talked a lot about all the different safety features in the cars, football helmets, I think I mentioned gymnastics mats, but all these different things that have some give to them, some cushion to them, that allow you to come to a stop more gradually. Because if you have more time to stop, there are smaller forces acting on you in a situation like this. So again, greater force, scenario 2, but they do have the same change in momentum. So again, question 1 was a calculation, which we'll work out now. And then we're going to get into today's notes, adding kinematics to our discussion. And then your assignment today, 502.3, is going to be just more impulse momentum theorem questions in that problem set. You'll have a problem set next Monday that does have kinematics in it as well. But for today, it's just going to be this one. So let's go ahead and go over number 1 in the warm-up, because that is going to be a question similar to what you're going to see in the assignment today. It says a 0.5 kilogram ball moving at 5 meters per second hits a wall and rebounds in the opposite direction at -2 meters per second. If the impulse occurs for 0.01 seconds, what is the average force acting on the ball? And guys, I wanted to give you this question because you had a similar question in your assignment yesterday, and several people were having problems with that question. I gave you a little bit more of a hint here than I did in the My Open Math assignment yesterday, and that hint is this negative sign. I didn't have to put that there because I already said it's in the opposite direction. But you had a question yesterday in the assignment that talked about a ball, I think it was a ball, hitting a wall and bouncing in the opposite direction. And some of you had trouble figuring out that the change in velocity, you had trouble finding that value because you weren't paying attention to the fact that opposite direction is going to mean that one of them is positive and one of them is negative. Okay, so if you had that issue with that question yesterday, you might want to go back and look at it again today. But let's go ahead and go over the warm-up question. And we're going to start by labeling the information we've been given. So we have a mass of 0.5 kilograms. We have an initial velocity of 5 meters per second. And again, because it goes in the opposite direction when it bounces, my final velocity is -2, not just 2. And again, this one's labeled that way, but the one yesterday wasn't. And some of you forgot to tack on that negative sign. The time of the collision, 0.01 seconds. So I have all of my given information, and I'm trying to solve for force. Looking at the information I have, I'm going to use this equation here. F times T equals M times delta V. That is impulse equals change in momentum. Okay, it's the equation that we talked about in our notes yesterday. Remember, delta V, change in velocity, is simply final velocity minus initial velocity. So I've plugged those numbers in. You're welcome to find the change in velocity first and then plug it in, Or you can substitute it in like this, VF minus VI. But this is where students, including some of you, are making mistakes, is in calculating your change in velocity, because some of you are looking at this and going 5 to 2, oh, my change is 3, okay, and it's not. Then give it like a number line or just look at the equation. But if you go on a number line from 5 to -2, that is not a change of 3, okay, or -3 for that matter. It is a change of -7. Okay, and you can see that if you plug it in here using the equation, final velocity, -2 minus initial, so -5, you're going to get -7. Okay, so that's where some of you had issues yesterday. Let's go ahead and solve this. Half of -7 is -3.5. Divide both sides by 0.01. -3.5 divided by 0.01 gives me a force of -350 newtons. And that is the answer to the first question on your warm-up. Does anyone have a question about this problem? All right, then please make sure that you have this put in on My Open Math for your warm-up question today, along with the other one that we talked about a moment ago. As I mentioned, we are going to be taking some notes today, and I say notes, it's really just some example problems more than anything else, because it's not new information. Okay, we're just going to be taking the unit, the stuff we've learned in this unit on momentum, and bringing back in kinematics. Okay, so it's not really notes so much as some examples. So again, I would copy these down, okay, so that you have them to refer back to. This one says a 1,179 kilogram automobile at rest accelerates uniformly at a rate of 3.0 meters per second squared for 20 seconds. What is the final momentum of the automobile? I don't know why I put automobile instead of car, but whatever. Okay, so again, as you read questions like this one, start by labeling the information you're given. I give you a mass. I gave you an initial velocity. The words at rest tell me that I start at a velocity of 0. I have an acceleration of 3 meters per second squared, and I gave you a time. Okay, and I'm asking you to solve for the final momentum. But in order for me to figure out my final momentum, I need to know my final velocity, because momentum is mass times velocity. And I've given you information here because I told you the acceleration and the time and the initial velocity. I've given you information that you can use to solve for VF, and then we can do a second step to find that final momentum. So we're going to use a kinematic equation, this one right here. VF equals VI plus A times T. You should recognize that one. We've used it a lot. And then once we find that final velocity, we can use the final velocity to find our final momentum. So it's going to take us 2 steps to solve this one. We're going to have to use kinematics to get VF, and then we're going to plug into our momentum equation. So let's start with that kinematic equation calculation. VF equals VI plus A times T. VI is 0. A is 3, T is 20, so it's 0 plus 3 times 20, or just 3 times 20, which of course is 60 meters per second. Okay, so now that we have a final velocity, we can go ahead and plug that in to the momentum equation. Final momentum equals mass times final velocity. Okay, since we're looking for the final momentum, we're of course going to use the final velocity to find it. The mass again was 1,179. The final velocity that I found just a moment ago is 60. All we have to do is multiply, and when you multiply those values together, you get 70,740, and my units will be kilogram meters per second. Kilograms times meters per second. So again, not anything new. In fact, it's something old. We use those kinematic equations since the second unit of the year, and we're still using them now. And that will happen again next unit too. Okay, so a lot of this stuff is going to come back, which is helpful because when you take your final exam, it won't be so rusty. You'll have seen it more recently. Okay, if you choose to take the final, but everybody has to take the TEAS test, so you got to use it there too. I know, get excited, Emily. All right, any questions about this one? No? All right, let's try something that looks like this. It says a 2.50 times 10 to the third kilogram car traveling to the north is slowed down uniformly from an initial velocity of 20 meters per second by a braking force acting opposite the car's motion. The coefficient of friction between the tires and the road is 0.25. And it has you doing a couple of different things here, drawing a free body diagram and then doing some calculations. So again, if you don't have paper out, you're going to want it out, because this type of question is what you might see as like a free response problem on your test. And again, if you haven't been paying attention, your test is 1 week from today. Okay, so you do need to know how to do stuff like this one. Okay, so I'm trying to look at the information I have here so that I can bring up my document camera so that we can work it out. Okay, so this is the information that I gave you in the question. Okay, I told you the mass of the car was 2.50 times 10 to the third. I told you that the initial velocity of the car is 20 meters per second, and I gave you a coefficient of friction. And the first thing that I asked you to do in this calculation was actually to draw a free body diagram. Okay, so let's go ahead and do that over here. Okay, and so I have my car represented here by a box, looks just like a car. And we're going to draw the forces acting on the car. I know that a good place to start is always to go ahead and just draw in that force of gravity, because it's going to be there every time that we draw a free body diagram, so long as we're on Earth, which we pretty much always are. Okay, I'm also going to go ahead and draw in my normal force, Fn. Okay, and I know that these will be equal and opposite to each other because my car is not accelerating. It's not going airborne. Okay, it's not accelerating vertically. Okay, and so I know that my vertical forces need to be balanced. It says that the car is traveling north and it slows down due to brakes and ultimately due to friction. So I'm just going to call north this direction over here. Okay, and so if I'm traveling that way and applying brakes, then my brakes need to be this way. Okay, so that's how I'm going to draw my force of friction, okay, or my braking force if you'd rather label it that. But I'm going to use force of friction because ultimately that's what the brakes are doing. Okay, and so I have these forces. The car's not accelerating forward, there's not any motion that way, it's simply slowing down, so that's it. I don't need an applied force or anything like that. Okay, so this is it for my free body diagram. So we've got the first thing, because the first part of the question said to draw the free body diagram showing the forces acting on the car. The second part of the question said what is the braking force acting on the car, and it says force of friction in parentheses, so it wants us to solve for this one. Okay, and again, force of friction we have an equation for. Force of friction is equal to my coefficient of friction times my normal force, or mu times Fn. Okay, and I have mu, it's right here. They gave it to me in the question, 0.25. But normal force, I don't have a value given to me for that. However, based on the diagram I drew, I know that the normal force is equal and opposite to Fg. And while I don't have an equation for this, I do have an equation for this. Fg equals mass times gravitational acceleration. So if we multiply the mass of this car, 2.50 times 10 to the third, if we multiply that times gravity, 9.8, we will get not just Fg but also Fn. Okay, and so that is going to be our next step. Now the mass that they gave me in the question is written in scientific notation, and you are welcome to leave it that way, or you're welcome to write it in standard form. Okay, 2.50 times 10 to the third kilograms is just 2,500 kilograms. Okay, and that might be easier for you to work with, I don't know. But if I want to go ahead and solve for Fg and thus for Fn, I need to multiply that mass by 9.8, and that's going to give me the magnitude of Fg and of course also Fn. So let's go ahead and do that. 2,500 times 9.8 equals 24,500, and so that is both Fg and that is Fn. Okay, and so let's go ahead and write it up here, 24,500 newtons. So we're going to take that number and we're going to multiply it by 0.25 because that's what this equation says to do. And so let's go ahead and multiply this times 0.25. And we get a force of friction of 6,125 newtons. And again, it's to the south. Since north is this way, it's opposite. Or you can label it with a negative sign. Either way, south, or you can put negative, oops, not a 2, negative 6125 newtons and call that the negative direction. All right. So we've answered the second part of the question. What is the braking force? That, okay, whichever way you chose to write it. The third part of the question says, what is the car's velocity after 2.5 seconds? So it wants us to find the final velocity after a time of 2.5 seconds given this information here. So we started with a velocity of 20 meters per second. We want to figure out how fast it's going after 2.5 seconds. That sounds like a kinematic equation, but I really need to know what my acceleration is. Okay, in order for me to use this kinematic equation, I need to have one more piece of information. So before I can actually solve for this final velocity, I first need to solve for acceleration and then for VF. And I have the information to find acceleration because if I look at this diagram, FF is my net force. It's the only force acting in the horizontal direction, and vertically I don't have a net force. I just found F net when I found FF. Okay, and so I can use this as my net force because it is the only force that's causing the acceleration. There's nothing else happening here. And I can use it along with my mass with this equation right here, F net equals M times A, and I can solve for A. Again, guys, I am bringing in everything we have done this year in the math for this problem. We're using kinematics, we're using forces, okay, we're using, or we will be using in a minute, momentum stuff. So it's a lot of steps, and there are a lot of equations. Okay, that is the hardest part of this class, not this problem specifically, but the fact that there is so much information given to you, and you have to say, here's what I know, what can I do with it? How can I get to the end goal that I'm looking for? Okay, and sometimes that just means solving anything you can solve for and then seeing what can I do with this, because you're going to have a list, a long list of equations, and you're going to be not sure necessarily which ones to use. That's why we label everything as well. Okay, but this is the hardest part. I know I'm walking you through it, but if I'm not walking you through it, you would have to know, oh, that's my net force. Oh, now I can find this. Okay, now I can find this. You'd have to be able to go through that thought process, and it's going to take practice. Okay, so you do need to make sure that you're doing that practice. Of course, we give you the classwork, but the unit summary would also be a good resource for that. Okay, back to this. F net. I'm going to go ahead and use the negative number. Negative 6125 equals my mass, 2,500 times A. I can solve for my acceleration that way. I already have that value in here, so let's just divide it by 2,500. And I do need to put a negative sign in front because I didn't type the negative. But my acceleration is negative, which makes sense because the car is slowing down. Okay, so my acceleration is negative 2.45 meters per second squared. All right, now that I have this, I can find what I was actually asked for in this particular part of the question, which is what is the car's final velocity? I know the initial velocity is 20, I know the time, and now I know the acceleration. I can use this equation right here, VF equals VI plus A times T. Okay, that's one of those 4 kinematic equations. So let's go ahead and plug into it. We're looking for VF. The VI, again, in this question was 20. The acceleration, I just found it to be negative 2.45. And the time was 2.5 seconds because that's what the question asked. It says, how far does the car move during the how fast is the car going after 2.5 seconds? Okay, so that was actually in the question that was on my screen a minute ago. So we need to multiply these first, and then we're just going to add 20 to it. Okay, so 2.45 times 2.5, again, negative 6.125, and then plus 20, because that's what it says, plus 20. and we get this. So our final velocity is equal to 13.875 meters per second. Okay, so we haven't stopped yet. We have slowed down, but we're not stopped. We're still moving forward. Okay, so that was part C of the question. Part D of the question is how far does the car move during that time? Okay, well now I have a final velocity, I have time, I have acceleration, I have VI. I can solve for delta x, and I have multiple options because I have several different equations, 3 of them in fact, that have delta x in them, but it's still going to be one of my kinematic equations. Okay, I'm just going to go ahead and use this one. Delta x equals VIT plus 1/2 AT squared. You don't have to use that one. That's just the one I'm going to use. Okay, you should get the same answer regardless of which formula you use, so long as you use it correctly. So my initial velocity again was 20. The time again 2.5 plus 1/2. My acceleration, again, we found that here, negative 2.45. And again, the time that was in the question, 2.5 squared. So VIT plus 1/2 AT squared. So let's go ahead and use the calculator to do this. All right, so we have 20 times 2.5 plus 0.5 times negative 2.45 times 2.5 squared. And that gives us this. And please check that negative sign that it's there, otherwise you will get the wrong answer. I get a displacement, delta x, equal to 42.344 meters. So again, how far? We're using a different kinematic equation. If I ask you how far, or how fast, if specifically this, if I ask you how far, you're going to have to use kinematic equations. That's the only place that that's going to show up. That doesn't show up in our momentum stuff. All right, the last question says, how long does it take the car to completely stop? Okay, so this was just what happens after 2.5 seconds. Now we're looking for how long does it take to get to a final velocity of 0 meters per second. Okay, so this is a different set of conditions. It's not going to be related to the previous questions really, although the acceleration I can use. Okay, the acceleration that I found was negative 2.45 meters per second squared. Okay, I have this final velocity. The question told me my initial velocity was 20 meters per second. So again, how long does it take the car to come to a complete stop? I can find the time. Again, kinematic equations. VF equals VI plus A times T, because that's what I'm looking at. Let me go ahead and move this so I have more space to write. All right, so we're down here now. Again, I found that acceleration earlier. I'm using it here because it's still the same situation with the same friction, the same car. So we get to reuse that. But otherwise, we're looking at a new final velocity. So 0 equals, again, VF equals VI plus A times T. 0 equals 20 plus negative 2.45 times time. And again, guys, for most of these, there's probably more than one way to do this, okay? I'm using kinematics here, but if you have the information, you might even be able to use, and I think you can, Ft equals m times delta V. And you might be able to solve for time here because we know the force, we know the mass, and we also have a change in velocity. So there's more than one way to do this. Okay, you don't have to use kinematics here. You could use this equation. But I already have the kinematic one written out. So we got negative 20 equals negative 2.45 times t. Negative 20 divided by negative 2.45. Those negatives are going to cancel. So 20 divided by 2.45 gives me a time of 8.16 seconds. Okay, so again, that's kinematics, but we already have the force as well. So if we wanted to do it this way, we found our net force from our brakes earlier to be negative 6125 times T equals, the mass was 2500 times delta V here is negative 20. And you could do it that way. It should give us the same answer. Okay, let's check and see if it does. Okay, 2,500 times negative 20 divided by negative 6125. Yep, there it is, 8.16, same exact thing. Okay, I told you there's more than one way to do these. So you could use impulse momentum theorem or kinematics to get that last step. Okay, questions? That's the whole problem, by the way. Are there any questions about this one? I know that's a lot of steps. Okay, so we're using a lot of different equations that we've learned over the course of the year. Let me go ahead and move this out of the way to answer these different parts. And there's more than one way to do it. Okay, more than one way to get there. Doesn't mean you're doing it wrong if you do it different than I do. Okay, as long as we end up with the same answer.
So is the first response of the test going to be like that, where it has like A, B, C, D?
It may have multiple parts like that. We will see. I have to look at it and see if I'm going to change it. In the past, yes. In the past, that's exactly what it looked like with multiple parts. This is that problem worked out by hand, so you're welcome to watch the video later if you want. But for the rest of the class period today, your assignment is 502.3 Impulse Momentum Theorem problem set. If you don't finish that during the class period, you can finish it for homework, but you guys have 20 minutes, so you've got a fair amount of time to maybe finish it or at least get a big chunk of it done. It's due by 11:59 p.m. if you don't finish it in the room. And then if you do finish early, I would strongly encourage you to work on some of that unit summary practice, because as y'all just saw, we just keep adding more equations and we're using all of the ones from the entire year, and that can get tricky. So it does take practice. And there might be more than one way to do it, just like the one that I just solved.
Next unit going to be adding more?
Yep, next unit's going to be even more added to it.
Next unit.
It's going to be work and kinetic energy. We're going to do the work energy theorem.
What about after that? More?
Yes, more after that too.